Dear all, this is the fifth video session of Basic Physics 2 lectures, and in this video we will review what we have discussed so far over some solved examples. The questions are uploaded on UK, so you can read the questions yourself. There are many questions actually, but I cannot cover the solutions of all of them in this video, but I'll pick up some of them and show you the solutions, and we will follow some discussions. We will review some discussions over these examples. Since my board doesn't have enough space, I'm not going to rewrite the questions. I'll read in this video, but again, you will have the questions, problems, so you can you can use the file of the questions to follow this video. The first example I'll pick up is the third question in the document. I'll just read it. In this question, we have two identical small spheres of mass 2 grams, and they are fastened to the ends of a 0.6 meter long, light, flexible, insulating fishing line. This fishing line is suspended by a hook in the ceiling at its exact center. I'll draw the figure so you will see it. The spheres are each given an identical charge, so we have two small spheres charged, but we don't know their charges. They are in static equilibrium with an angle of 30 degrees between the string halves. And the question is about the magnitude of their charges. So I want to also discuss the strategy and our approaches when we have some problems. Actually, we shouldn't hurry on the solutions. First, we need to understand the problem, as we discussed in the class before, and what an understanding is. Actually, following some steps. And the first step is actually picturizing the problem. So let's see what we have in the problem. We have a fishing line. Actually, this is insulating, so the charges cannot move from one sphere to another one over the line. That is why we choose an insulating fishing line. So this fishing line is hooked on the ceiling. This is the ceiling, and we have a hook here. So we just hook the fishing line. This is fishing line, and two small spheres are fastened to the ends of this fishing line. The masses are 2 grams, and they are identical. And since the total length of this fishing line is 0.6 meter, 1/2 will be here, like 0.3 meter, and 0.3 meter for the other half. And this system, they have some charges, Q and Q. Since they are identical, we assume the Q's are the same and they have the same sign. Actually, if it is positive, the other will be positive. If it is negative, the other will be negative. And they are in static equilibrium in this system. What the static equilibrium means, actually they are not moving, they are in balance after we adding all forces acting on the small spheres. And the question is asking what is Q. So let's first summarize what we have from the the problem. So this is 30 degrees. So we have M's, M1 equal M2, that is equal to gram. Just keep in mind, we are not using gram in SI units, so we are going to convert it to the kilogram when we start the solution. And what else? They have some charges. The length here like 0.3 meter and 0.3 meter. Here the angle is 30 meter, and since they are identical, they are symmetrical. And the question is, what is Q? There is no way we can find the sign of Q, negative or positive, because in both cases, since they have identical charges, the electric force between them will be repulsive. So the question is asking the magnitude of the electric charge. Okay, so this is the first step. We picturize the problem, we summarize what we have and what is asked in the problem. The second step in such problems, actually, it doesn't matter how simple they look, we need to start by drawing free body diagram. Okay, if we have any problem, mechanical problem, including forces or any kind of forces, we should start with the free body diagrams. So first, let's start with the free body diagrams before solving the charge Q. Let's say this is the first object and this is the second object, and the free body diagram for the first object, this dot representing the first mass. So we need to show all the forces acting on the first mass. So it has a mass, so gravitational force is acting on it, like minus mg. I mean, I didn't put minus here because I already showed the direction. And another force, the electric force, due to the other charge, and since they have identical charges, the electric force F will be repulsive, so in this direction. And we have the tension on the string, let's use it T1. Okay, so this is the free body diagram. FBD stands for the abbreviation for the free body diagram 1. And then for the second one, again, this dot representing the second sphere. So now we need to show all the forces acting on the second sphere. All right, again, it has a mass, so gravitational force is acting on it. Again, since they have the same masses, I put mg. And the electric force due to the first sphere, charged sphere, so the force is repulsive. The electric force for the second sphere will be in this direction because it is repulsive. And by Coulomb's law, we know the electric forces will be equal, but in the opposite directions, like action-reaction forces. And now again, the tension T2 on the fishing line. Actually, it will be easy to see T1 will be equal T2, but in the beginning I just wrote them like different forces. So they are different forces because they are in the different directions, but we are going to find that their magnitudes are equal. Okay, so from the let's little bit use the geometry to here. Since these are identical, and if I just put a half line here, 30 degrees here, 15 degrees will be this side, and the 15 degrees will be in the other side. So if I put I put a coordinate system like this is y direction, this is x, this angle will be 15 degrees, and similarly here, if I put the coordinate system here, this angle will be 15 degrees. Or we can also write this angle is going to be 75 degrees. Okay, you are free to use any of them. Either you can go with 15 degrees or you can go with 75 degrees, but you need to be careful in using cosine and sine once you pick up the angle. All right, so let us write the equations from the first free body diagram. Since they are in static equilibrium, the total force should be zero. The total force acting on each sphere should be equal 0. So along the y-axis, we have T2, T1 times its vertical components will be cosine 15 or sine 75 if you use 75, and minus mg should be equal 0. Why minus mg? Because it is downward and mg is its magnitude. The second equation, also the horizontal components of the total force should be equal 0, and we have horizontally T1 times sine 15 or cosine 75 minus Fe, the electric force, should be equal 0. And from the second free body diagram, we are going to have again the similar equations. So let's look at the second free body diagrams. Again, the second sphere is in static equilibrium, so the total force on it should be equal 0. So along the vertical axis, we have T2 times sine 15 minus mg should be equal 0, and horizontally we have minus T2 times cosine 15 plus Fe equals 0. Why we switch the signs in compared to the second equation of first free body diagram? Because now the horizontal component of T2 is in the negative direction, while the electric force on the second sphere is in the positive direction. And just before cleaning up this board to make myself some space, let's compare these two equations. Actually, the first equation here is identical to the first equation from the first free body diagram. But the only difference is T1 and T2, but mg's are the same because the spheres have the same masses. And the second equation, except the signs, the second equation is identical to the second equation of the free body diagram. The only difference, except the signs, the only difference is T1 and T2, but both are equal 0. So to satisfy all these equations simultaneously, T1, the magnitude of T1 should be equal to the magnitude of T2. So afterward, I'm going to call it only T. All right. So this is the free body diagrams. Just keep in mind we are going to use them. And again, it doesn't matter how simple the problem looks. You need to first draw the free body diagrams and make sure you are not missing any force. So you can check for a few seconds if we are missing any force, but this system is simple and it is easy to see. Actually, we included all the forces in the free body diagrams already. All right. To find now the strategy. Actually, the question is asking about the charge Q, but here we have including only the electric force. How we can go to the electric charge by using these equations? Actually, the key parameter is the electric forces. If we know the electric force between these two spheres, then we can go to the electric charge by using Coulomb's law. Okay. Now, from the first equation here and here, now I'm using T instead of T1 and T2. T times sine 15 will be equal mg. And from the second equation, again, from both free body diagrams, T times cosine 15 will be equal the electric force. And by using this, from here, I can write T is equal, or, okay, just 1 second, not sine, it's going to be cosine here, and it's going to be sine here. All right, so this is cosine, this is sine, and from here I can write T is equal mg over cosine 15, and if I use this equation in the second equation instead of T, if I replace T with this equation, so I will find mg over cosine 15 times sine 15 will be equal the electric force, and from here the electric force will be equal mg times tangent 15. All right, we got the electric force by using Newton's laws and also free body diagrams in terms of the masses, the gravitational force mg on the spheres, and also the tangent of the angle of 15. Now, what else we have? Actually, we also have this force, the same force by Coulomb's law. So Fe we know also will be equal K times Q1 times Q2 over R squared. And here we know Q1 is equal Q2 equal Q. What about R? We can also find R by using some geometry. All right, so this is the ceiling, right? And this is our system. And this is the distance between two spheres, which is going to be used in Coulomb's law. But what is R? We know the 1/2 is 0.3 meter. If I just draw a normal to the bottom of this triangle, like the angle between this line and the bottom will be 90 degrees. So it's going to be r half, and this side will be called r half. So by using Pythagoras theorem, we can find what is r half. So it's going to be like 15 degrees. And by using here, let me just follow my notes. by using the geometry here, the sine of 15 will be equal r half over 0.3, or from here r will be equal 2 times 0.3 meter times sine 15. So I mean, we know what is sine 15, and 2 times 0.3 meter times sine 15 will give you the magnitude of r. And if you plug the numbers by using your calculator, you will find that r will be equal 0.15 meter. Alright, so we are going to use 0.15 in Coulomb's law to find what is the electric force. And we know this electric force also from here. mg tangent 15. All right, we are almost there. So we are going to use this, like F, electric force F will be equal electric force F. So this is just a trivial equation, but one side will include this equation, while the other side will include Coulomb's law here, this equation. So Fe from our free body diagrams will be equal mg tangent 15, and the right hand side of this equation will be equal k. I'm going to write q squared because q1 and q2 are equal q, and over r squared, and we know what is r already by using geometry. And from here, let me just make myself some more space. From here we need to have what is q. So q, so I can take q squared out of this equation as mg tangent 15 over k times r squared. And if I plug the numbers here, the q squared, if you put like 2 grams, or let me just try to write, m was 2 grams, but we need to convert it to the kilogram, and g is 9.81 meter per second squared, and tangent 15 over k is equal 8.99 times 10 to 9th. What was the unit? Newton meter squared per Coulomb squared, and times r squared. R squared is 0.15 meter, so I don't have space, I just put r squared here, but r is equal 1.15 meter. And if we plug all the numbers and use the calculator, we find q squared will be equal 4.9 times 10 to minus 14 Coulomb squared. To find what is q, we just need to take the square root of this number, like square root of 4.9 times 10 to minus 14 Coulomb squared, which will give you 0.2 times 10 to minus 6 Coulomb. 10 to minus 6 actually is for the micro, so we can also write this q will be equal 0.2 micro Coulomb. And this is the answer of this problem, the third problem in our document. Alright, so this is actually simple, but let's just summarize what we had. First of all, you need to picturize the problem. Second of all, you need to, if you have some problems like mechanical problems like balance or acceleration, the forces acting, forces in motion, you need to start with free body diagrams. It doesn't matter how simple the problem looks. First, draw the free body diagrams for each object in the system. Here we had 2 spheres, so we would have 2 free body diagrams. Then, since they are in static equilibrium, the net force acting on each sphere should be equal 0. So got the equations from free body diagrams and then start solving. And the strategy is the important. Actually, we didn't jump to the electric charge. We first calculate the electric force by using the equilibrium equations, and we found mg tangent 15 will be equal to the electric force. But the other side also, we know Coulomb's law to write the electric force in terms of the charges of spheres, and this is the door we can move from the mechanic to the electricity and magnetisms, and then just following some mathematical steps, use your calculator, we found each sphere has 0.2 microcoulomb charge. Indeed, actually the problem told us that the spheres have the identical charges, but it doesn't have to be identical. From Coulomb's law, we know the electric force will always be equal mutually. So we could give you like the one sphere has 3 times as charge, 3 times as much as the other one. Still the solution will be the same. You just need to put the Q appropriately there. All right, actually this is an example about Coulomb's law. Now we are going to move to the electric flux and Gauss' law to solve some problems. Now we are going to take question 6, problem 6 in the document, so you can read it, I'll read it for you. Now in problem 6 we have the square surface, and one side of the square surface is 3.2 millimeter. Since it is square, all sides will be equal, and this square is this square surface is immersed in a uniform electric field with the magnitude of 1800 Newton per Coulomb. All right, uniform means constant electric field. So electric field is same everywhere, it doesn't change. And the field lines, I mean, we put this square surface in an electric field such that the field lines make an angle of 35 degrees with the normal to the surface. And the question is asking us to calculate the electric flux through the surface. All right, first, picturizing. We have a square surface. Let me just put it with red. So this is the square surface, and each side has 3.2 millimeter. Actually, there are many electric field lines, but I'll draw only one of them to picturize it. It is in an electric field, so this is one of the electric field lines representing the electric field. Uniform, so electric field is equal, let me make some space here. Electric field is equal 1800 Newton per Coulomb, and it is constant. This is just the magnitude. Line shows you the direction of the electric field. And if we draw the normal of this electric field, of this surface, let me just, this is the normal. Make a right angle, 90 degrees angle with the surface, and it makes 35 degrees with the electric field. And asking what is the electric flux through this surface. And let me remind you the definition of the electric flux. Actually, electric flux through a surface is illustratively the number of electric field lines perpendicularly passing through the surface. This line is not perpendicular to the surface at all, right? Actually, it makes some angles, so we need to consider its component, perpendicular component to the surface. So the definition of the electric flux phi is nothing but the scalar multiplication of the electric fields and the area vector. And you remember area vector. Area vector has a magnitude which is equal to the area of this surface, but its direction is perpendicular to the surface. So if I write a unit vector n hat, which is perpendicular to the surface, actually this is in the direction of the normal, so I can write vector A, like A, its scalar magnitude, which is equal to the area of this surface, and n hat gives you the direction. Okay, direction is perpendicular to the surface, and you know the area, how to calculate the area of this square surface. This is just the multiplication of two sides, like a times b, but this is a square, so a times a squared, a is equal to 3.2 millimeter. We need to just convert it to the meter to use SI units. Okay, so the phi electric flux is simply equal to the scalar multiplication of the electric field and A. So using the definition of the scalar multiplication, I can write them in terms of the magnitude of the electric fields, magnitude of the area times cosine theta. Theta is the angle between them, so it is 35 here. Okay, so what is, I can use this. You don't need to integrate anything because electric field is constant through the surface, so it is just simply the scalar multiplication. The magnitude of electric field is equal 1800 Newton per Coulomb. The area is simply the square of this side, but we need to convert it to the meter. So 3.2 times 10 to minus third meter squared times cosine 35. And if you use your calculator, you will find the value of the flux, which is equal to the 0.015. And you shouldn't forget the units, Newton per Coulomb times meter squared. So this is the electric flux passing through this surface. All right, it is a simple problem, but the main point, while we were discussing the electric flux, the main point is Gauss law, and we already discussed how useful the Gauss law is, and then we use them. Now we are going to move to the Gauss law, and I'm going to solve you a trick, actually easy but tricky question, which is given in problem 7 in the lecture. In the problem 7, we have a point-like charge of 1.8 microcoulomb. You should convert it to the coulomb and you use it in your equations. And this point-like charge is placed at the corner of a cube, all right, whose sides are 1 meter long. So each side is 1 meter long of this cube, but the point-like charge is placed at one corner of this cube. So using the Gauss law, first calculate the total electric flux through the cubic surface, and then also in the second part, part B, is asking to calculate the electric flux through each surface. So let's first picturize the problem. We have a cubic surface, right? And remember, to use Gauss law, we need to have a closed surface, and in this problem, the closed surface, the Gaussian surface, is a cube. And then for this problem, I need some space. So I'm going to draw it here. So we have a cube here, right? This is a cube. And we have our point-like charge over here. Let's call it Q for now. Now, this corner actually is not inside the cube, but is not outside the cube. So how we are going to use this the Coulomb's law to calculate the electric flux? To use Gauss law directly, actually this charge should be enclosed inside the surface anywhere, but it is not inside, it's not outside. So it's not straightforward to use Gauss law in this shape. But we can use a trick actually. What if we have a larger cube, all right, a larger cube, and we have this point-like charge at the center of this larger cube, then we could use Gauss law. So why not we don't have a larger cube? I'm going to complete this cube to a larger one by adding some more cubes, but identical to this one. So if I add another cube like this, okay, actually I don't have this cube in reality. All right, this is second cube and another one. And another one, okay. So we already have like 3 more cubes. Actually, it's now larger one, but still it is not at the corner now of this larger cube, but it is on the side, still on the boundary. All right, it's not inside, it's not outside. So I need to put another 4 cube like this, okay, through U, from the board through U, And then we are going to have in total 8 cubes of this one, identical to this, my real cube. Then if I put 4 more cubes like this, you are going to have 8 cubes and this point like charge at the center of this large one. So for the 8 cubes, let me just make some notes. If we complete this cube to a larger one by adding, how many cubes we added? 3 here and 4 more, 7 cubes, 7 identical cubes. Adding 7 more cubes identical to 1 given in the problem. Then we could use Gauss law for the large one. And Gauss law, what Gauss law says? The total flux through the large cube. Because large cube is a closed surface and this point-like charge is at the center of this large cube. It will be simply the total charge enclosed over epsilon 0. But this is the total flux through the large cube. And actually, since they are identical and the point is at the center, each cube share this total flux equally. So this is the total flux through the large cube, but the phi will be like the 1/8 of the total flux, since we have 8 cubes in total and this is one of them. So actually this is the total flux q over epsilon 0 through the large cube, and this is 1/8 of it. 1/8 of the total flux will be the total flux through this surface. So what is total flux here? Like q over epsilon 0. So I can write the flux through this, our main cube, will be equal 1/8 of the total flux, which is equal q over 8 epsilon 0. You know the value of q, which is given in the problem. Epsilon 0 is a constant, so you can use it to, and using your calculator you can get the answer. So I'm just going to write the answer for you. Let me just check my notes. It's going to be 25.4 Newton per Coulomb meter square. So if you put Q is equal like 1.8 microcoulomb, don't forget to convert it to the Coulomb, and A over 8 epsilon 0 will give you this value for the total flux through only this, our main cube. All right, we use a trick to complete it to a larger cube, but the other cubes, 7 more cubes, are not real. Okay, they are like fake cubes. We just add them by hands to be able to use Coulomb's law, but we need to get back to our main cube. Okay, which can be obtained by dividing the total flux by 8 and then put the total flux here by using Coulomb's law. You will get this number. Okay, the second part is asking calculate the electric flux through each surface, each face of this cube. So this cube has 6 faces and we are going to calculate one by one, but actually it's going to be easy. So let me just draw again our cube here, the second part here. Okay. All right, and our charge is here, Q. Now let's look at the faces one by one. First, the top. Actually, this charge will generate some electric field. We can show this electric field by lines. So it's going to be like this, or this, or this. Now this corner actually meets three sides. The bottom, the front, and also the left side. But the electric field lines will be parallel to the surface to these 3 surfaces. Electric field lines will be parallel to the top surface. There will be no perpendicular component of the electric field. Also, it will be parallel to the front face. Okay, the electric field doesn't have any perpendicular component, perpendicular to the front face, and similar to the left face. Okay, so since there is no perpendicular electric field for the top, front, and the left faces, the electric flux phi through this three surface will be equal 0. Okay, for top, front, and left faces. Now we have three more faces. All right, bottom, back, and also right faces. For this, so this surface, actually the electric field has perpendicular components through these surfaces. Okay, for back or for bottom, back, and right faces. These three faces actually will share the electric flux through this surface equally, and then like we already calculated phi, which is equal Q over 8 epsilon 0, and each face, each of these three faces, bottom, back, and right, each face shares it equally. Alright, so how we are going to write? Face bottom will be equal face back will be equal face right, and since they are equally, it's going to be phi, the electric flux through this cubic surface over 3. And if we plug this total phi through this surface here, we are going to find phi side for back, for bottom, back, and right will be equal Q over 8 epsilon 0 times 1/3, which is going to be Q over 24 epsilon 0. And Q is given in the problem. It is 1.8 microcoulomb, 24, and epsilon 0 is again dielectric constant of the empty vacuum or empty space. So you can plug its value here, and you will find for each side of bottom, back, and right faces will be equal 8.5 Newton per kilometer square. And it's gonna be the answer of the second part as well. Alright, so let me summarize what we did. In the beginning we had a cubic surface, actually it's a closed surface, but our point-like charge was placed at one corner of this cube. So question was asking us to calculate the electric flux through this surface and also from each side by using Gauss law. But in this case, since the cube is not directly inside of this cube, we couldn't use Gauss law directly. We need to use some tricks to be able to use Gauss law, because this corner is on the boundary. It's not enclosed. I mean, it's not inside, but it is not outside either. So we need to use some trick to be able to use Gauss law, and the trick was to complete this cube to a larger one, such that that point-like charge was placed at the center of a large cube. And we could use Gauss law for that large cube, and we used it. We find the total flux through the large cube by using Gauss law, and then get back to this cube, because this is the real one. This is given by the problem. The other 7 cubes were fake. We just put them to be able to use Gauss law. We need to get back to our main cube, and it is just 1/8 of the total flux to the large cube. So we find it like Q over 8 epsilon 0 will be the total electric flux through this surface. Then each side, we need to be careful to get the electric flux each side, because some faces, the electric field lines are just parallel to some surfaces of this cube. And in the picture we showed it, actually the top face, front face, and the left face doesn't have perpendicular electric field lines. So actually the electric flux is not going through these surfaces. And the rest of the 3 faces, bottom, back, and right, we could calculate some non-zero electric fluxes, but they are sharing the total electric flux through this surface equally. And then we just need to divide the electric flux by 3, and we found it's going to be equal Q over 24 epsilon 0. And if you plug the numbers here, you will find 8.5 Newton meter squared per Coulomb for the electric flux for each phase. Each phase means each phase of bottom, back, and right. Alright, this is how we can use Gauss law, even though it seems not appropriate in the beginning. Now we are going to get the ninth problem in the document. Let me clean this up. All right, problem 9 in the document. Let me just correct this. Problem 9. Actually, the problem 9 is a simple problem. Just refresh some discussions we followed in the lectures. In the problem 9, we have an isolated conductor of arbitrary shape. This conductor doesn't have a certain geometrical shape. It is arbitrary, and it has a net charge of 10 times 10 to minus 6 Coulomb, or 10 microcoulomb. And there is a cavity inside the conductor, and within this cavity there is a point-like charge of 3 times 10 to minus 6 Coulomb, or 3 microcoulomb, and it is asking what is the charges first on the cavity wall, and B, the second part, on the outer surface of the conductor. So first, let's picturize the surface conductor. So we have a conductor of an arbitrary shape, and just remember this conductor has a net charge Q net, let's call it 10 microcoulomb, or you can say 10 times 10 to minus 6 Coulomb. All right, and just remember conductors doesn't like electric field inside them, so all these charges will be accumulated on the surface of the conductor, and by using Gauss law we can say if the charges are on the surface, the electric field inside was equal to 0. We discussed this by using Gauss law in the second or third video of our lectures. But this is not the whole picture. This conductor has a cavity inside it. Let's say here, the cavity also has an arbitrary shape. So, and there's a point-like charge Q in this cavity. So, again, the Q is also given. Q is equal, let me just check the number again, 3 microcoulomb. All right, or 3 times 10 to minus 6 Coulomb. Now, again, the conductors doesn't like electric field inside it. They want it to be 0. They want the electric field to be 0 inside itself. So, but if I draw a Gaussian surface now inside it, any Gaussian surface, but I just choose the spherical one because the shape of the surface is not relevant. Because due to this, if I get this Gaussian surface, because of this point-like charge in the cavity, there will be some electric flux through this surface, right? And since we have non-zero electric flux, it means there should be an electric field, non-zero electric field inside it. So first of all, let me remind you, the conductors, the electric field inside the conductor should be 0. So in this case we have non-zero electric flux. It means the electric field is not zero inside the conductor, but conductor doesn't like it, so it is going to react to make electric field 0. How it is going to react? It's going to put some electric charges on the cavity wall, like minus Q. All right, it's going to distribute this minus Q over the wall of the cavity. So if I draw this Gaussian surface again, what is the total charge? If I write the flux through this Gaussian surface, it's going to be Q total over epsilon 0, and Q total now, Q minus Q over epsilon 0, which is going to be 0. So the conductor, once, if it has some cavity and with some point like charge inside it, the conductor puts the negative our opposite sign of the total charge over the cavity wall to make the electric field zero inside it. See, the electric flux, if the conductor puts minus Q and distribute it over the cavity wall, then the total charge inside this Gaussian surface will be equal 0, Q minus Q, and the total flux will be equal 0. It means the electric field will be 0 again. So the answer of part A of this problem, for A, the charge on the cavity wall will be minus Q, and which will be equal minus 3 microcoulomb, or 3 times 10 to minus 6 coulomb. Then, just by discussion, we answered part A of this problem, because, I mean, you shouldn't forget this, the electric field inside the conductor has to be equal 0. Even though you put a charge in the cavity, even though you try to generate an electric field inside the conductor will react against it, and it puts minus the opposite sign of the total charge over the wall of the cavity to maintain the electric fields at 0 inside it. Okay, so the answer will be minus Q, the charge on the cavity wall will be minus Q, which is simply minus 3 microcoulomb. Alright, now part B asking what is the charge, let us call it Q, what is the charge over the outer surface of this conductor. Now Q net is given, the total charge of this conductor is given like 10 microcoulomb. Actually, if there was no cavity, this whole charge would be distributed over the surface, but the conductor sent some of them to the cavity. So Q net, part B, Q net should be equal Q outer surface plus Q cavity. Alright, so we already calculated what is the Q cavity, so minus 3 microcoulomb, and we don't know what is Q outer surface, and it should be equal 10 microcoulomb. And rest of the part, actually, if Q should be equal 13 microcoulomb, right, 13 microcoulomb minus 3 microcoulomb will give you the net charge of this conductor. So in part B, the charge of the outer surface of this conductor will be equal to the 13 microcoulomb. Actually, this is a simple problem. Just you need to know the electric field inside the conductor should be 0. Then you need to see how it reacts if there is some charges inside it, and that charge will generate some electric field which conductor doesn't like, so it's going to react against this electric field to put the same amount but opposite charge on the wall of the cavity to maintain 0 electric field inside it. So no calculation, just knowing, and then you can directly say the total charge of the cavity wall should be equal minus 3 microcoulomb, and then total charge of this conductor is given like 10 microcoulomb. So you can find the total charge distributed over this surface, outer surface, by just taking this, like Q net will be equal outer surface charge plus cavity charge, and it will give you 13 microcoulomb. Alright, so this is for problem 9. Now we are going to get to the subjects of the motion in electric fields. Let's take a break here, 5 minutes, and I'm going to continue to solving some problems for the motion in electric field in the second part of this video. Hope you enjoy. Okay guys, let's continue with the 11th problem in the document. 11th problem is the first problem about the motion in an electric field, and actually it has many parts to ask. It is a good review. Also the motion, Newton's laws, as well as the electric field. Now in the 11th problem, we have 2 charge plates. I put in the figure like this, like plus Q is here, minus Q is here. We don't know what their charges, but we don't need to know. The problem gives the separation between these 2 plates as 20 millimeter, and here we have 1 electron and 1 proton in the midway. So the electron and proton is 10 millimeter below the first place, the positively charged. Also, the electric potential difference between two plates is given as 100 volts. So I choose this point A, the potential at this point A, 0 volt, and at point B, the VB is 100 volt. And actually it is, as I said, this problem has many parts to provide a good review of the motion, Newton's laws, and how we can use them when the charged objects are in an electric field. Before starting to solve these problems part by part, let's first see what we can get more from this problem. All right, so here let me call this point C. All right, this is point C, the midway where the electron and proton are placed, and I'm going to call C. So that at this point the electric potential will be Vc. We can calculate it easily, but even though we don't know what the charges are, we can calculate the electric field in between these two plates. And remember, when we calculate the electric field of a plate, charged plate, we can treat this like the infinite plates. The electric field, it was constant. We found the electric field was constant. And if we put two plates, so the electric field is just depending on the charge. Also, but we don't know the charge, so we cannot use these charges to calculate the electric field. But from the discussion of the electric potential, also we know the electric potential difference between point B and A will be equal to the electric fields times the separation. All right, and we know the separation, we know the electric field difference between points B and A. So 100 volt will be equal to electric fields times D. D is the separation, and we know it is 20 millimeter. Just we need to convert it to the meter to use in this equation. So it is going to be 20 times 10 to minus third meter. And by using this equation, we can find the electric field as, let me check my notes, 5,000 Newton per Coulomb. And we know the direction of the electric field, right? The electric field lines are getting away from the positive charges and getting toward, coming toward the negative charges. So this is the direction of the electric field whose magnitude is 5,000 Newton per Coulomb. All right, I mean, it's not asking the question, but it might be useful, so let's just put it here. And else, we can also calculate the electric potential at point C. So Vc, the electric potential difference, let me call it like Ca, which is going to be Vc minus Va, which is going to be equal to the electric field times d prime, right? Because the separation between the point C and A is 10 millimeter d prime. And we know now electric field, we know d prime, but we don't know the electric potential difference at point C. So we can plug what we found into this equation. It's going to be equal 5,000 Newton per Coulomb times 10 times 10 to minus third meter, and you will find it, let me just check my notes. Okay, 5,010 millimeter, it's going to be like 50 volt. All right, so it's going to be 50 volt. The electric potential will be 50 volt at point C. Actually, it is also easy from A to B. If it is 100 from A to midway, it should be at 50 volt, right? So it is a proper calculation, but you can see it easily from the figure as well. All right, so from the problem, what we have two parallel plates, charged parallel plates. One is charged positively while the other is charged negatively. The charges, total charges used here are equal and the plates are identical, so they have the same area, and the separation between two plates is 20 millimeter. We have an electron and proton in the midway, so they are going to move in the electric field generated by these two plates, and we could calculate the electric field between the plates is equal to the 5,000 Newton per Coulomb. And also we can calculate electric potential difference along the midway, which is found 50 volts. This is what we have from the problem. Now, first part, let's keep in mind these numbers because we can use in our calculations. So first part is asking the location of the electron and proton after they move 5 millimeter. All right, location of electron and protons after they move 5 millimeter. Now, we don't need to calculate anything, just we need to use what we know so far. Now, we have electron, which is carrying negative charge, elementary charge, remember, and the proton, which is carrying positive charge. I mean, the magnitude of the charges are equal, but opposite sign. So what happens if two objects are carrying opposite charge in the same electric field? Remember, negative charges are moving in the opposite direction of the electric field, while the positive charges are moving in the same direction of the electric field. So after they move 5 millimeter, actually, the electron will move upward through the positively charged of the charge plate, while the proton is moving downward through the negatively charged plate. So after they move 5 millimeter, the electron will be here. Let me just, this is the place of electron, and actually it was 10 millimeter in the beginning. Once after electron moves 5 millimeter upward, this size will be 5 millimeter. And for the proton, it's going to move downward, and after it moves 5 millimeter, it is 10 millimeter again, so it's going to be 5 millimeter above or 15 millimeter below the positively charged plate. So the location of the electron after they move 5 millimeter, it will be 5 millimeter below the positive plate, and proton will be 15 millimeter below the positive plate. Why we wrote them with respect to the positive plate? Because we put our origin on the positive plate. Okay, the position of the electron and proton then should be defined with respect to the positive plate. So 5 millimeter below the positive plates, the electron location, and 15 millimeter below the positive plate is the proton's location. Okay, this is the answer of first part. Now the second part is asking calculate the electric forces acting on the electron and proton. All right. Now the forces, again, we are going to use the definition of electric field and and the relation between electric field and electric force. So B is asking the electric forces on the electron and proton. So electric force on the electron, let me call it Fe, will be equal QE, the charge of the electron, times the electric field. See, I mean, we need to write a vector equation because force is a vector. We need to derive the directions of this vector. So QE is negative E. You know what is E actually, 1.602 times 10 to minus 19 Coulomb, the elementary charge, times the electric field. See, I mean, the electric force on the electron will be in the opposite direction of the electron, so of the electric field. So this is gonna be Fe. And if you calculate it, we just plug the numbers here. If I write, it's going to be minus 1.602 times 10 to minus 19 Coulomb times the electric field is 5,000. We calculated it, remember, Coulomb, but the direction is minus J, right? Because it is downward. And if I write the result, it's going to be 8.01 times, let me just check my notes, 10 to minus 19 Newton. Okay, this is the electron force, electric force on the electron. Now, similarly, we can calculate the electric force on proton, and it is going to be like the multiplication of the charge of the protons times the electric field. And we know the proton has a positive charge, so the force will be in the same direction as the electric field. So the force on the proton, electric force on the proton will be downward here. And actually the magnet of the charges are equal to each other, just the sign is different of the electron, between the electron and proton charges. So QP, the charge of the proton, is simply the elementary electric charge times the electric field. And this E is equal 1.602 times 10 to minus 19. Electric field is the same. So the value will be the same here, 8.01 times 10 to minus 19, but it will be in the opposite direction. So I can directly write the electric force of the proton will be minus 8.01 times 10 to minus 19 Newton, and in the direction of J. I forgot here J, and here J. See, this negativity is about the direction, and direction is direction of the electric force on the proton is downward along the negative y-axis. So we have a negative sign here, actually because our electric field is downward. So once again, the electric force on a negatively charged object, here is electron, will be in the opposite direction of the electric field, while the positive charge objects, the electric force will be in the same direction as the electric field. Okay, it was part B. Now the third part is asking what are the accelerations of electron and proton under these forces, and we need to use Newton's second law to answer this problem, right? So let me just clean up here for part C. All right, C is asking the accelerations of electron and proton. We already calculated the force in part B, so we can use Newton's second law. Newton's second law, F will be equal to the mass of the objects times its acceleration. So we need to know what are the masses for electron and proton, and we are using this Newton's second law as we did in mechanics while we were discussing mechanics. So we are going to use the masses in unit of kilograms. So let me remind you the units of mass of electron. ME is the mass of electron, and I can write it 9.11 times 10 to minus 31st kilogram, while the proton mass, actually proton is about 2,000 times heavier than electron, and I can write it 1.67 times 10 to minus 27 kilogram. We are going to use this. All right, let me clean up this part. I'm going to draw it again when we need it. All right, so if I start with the electron, from here, let me write it. The acceleration can be written F over the mass. So I'm going to use this equation. For electron, let me use blue. For electron, AE is the acceleration of the electron, will be equal FE over ME. And what we find for FE, it was in the positive direction, vertical direction. So 8.01 times 10 to minus 19 Newton, J, over electron mass, which is 9.11 times 10 to minus 31st kilogram. And if we use our calculator, we are going to find the acceleration of the electron will be equal, let me see, about 8.8 times 10 to 11th meter per second squared. So this is, of course, the direction will be positive, right? Because FE is in the positive direction, and by this equation, m is always positive, so acceleration and force should be always in the same direction. Okay, the similar calculation but for proton now. Alright. AP, the proton acceleration, will be equal the electric force on the proton over proton mass. And again, the forces were the same on the electron and proton, but in the opposite direction. So minus 8.01 times 10 to minus 19 Newton J over proton mass, which is 1.67 times 10 to minus 27th kilogram. And if you use your calculator, you will find the acceleration of the proton in the negative direction, because force is in the negative direction, and the value will be equal 4.8 times 10 to 8th meter per second squared J. And again, see, actually proton is accelerating downward while the electron is accelerating upward, as we discussed in the first part when we locate them after they move 5 millimeter. Alright, so now the next part, part D, is asking the time of their travel after they move 5 millimeter. Okay, and now it is about motion. Let me just clean this up. Part D is asking travel time through 5 millimeter for electron and proton. Now let's first write the equation of motion for an object which is moving with the acceleration, constant accelerations, because the electric force is not changing. So x, the position, or let's say y here, because we are using vertical axis, will be equal y 0, the initial position, plus their initial velocity times time, plus 1/2 their accelerations times t squared. And actually y0 is 10, remember in the figure, like if I draw it here, they were here in the beginning, right? It is 10 millimeter, it is 0 millimeter, it is 10 millimeter, it is 20 millimeter. Alright, and after that, their final, electron's final position will be equal 5 millimeter, while the proton's final location will be 15 millimeter with respect to our origin. So in general, actually, I can write here this equation like y minus y0, which is equal delta y, and actually they are starting from rest, so v0 is equal 0. I can write 1/2 a t squared, and delta y is equal 5 millimeter in our problem. Of course, we need to convert it to the meter before using it. So for electron now, delta y which is equal 5 millimeter, will be equal 1/2 the acceleration of electron times t electron squared. This t electron is the travel time of the electron, and from here t electron squared will be equal 2 times delta y electron over acceleration of the electron. And it is actually we are going to use the absolute value of the accelerations, because we use the absolute value, but okay, y delta y is equal y minus y0, we are going to say it. All right, so it is going to, for electron, it's going to be like 2 times 5 millimeter, delta y is 5 millimeter, but 5 times 10 to minus 3rd meter over acceleration. What was the acceleration for electron? Which is equal 8.8 times 10 to 11th meter per second squared, and t squared will be equal about like 1.1 times 10 to 14 second squared, but we need to take the square root. So if you take the square root, the travel time of the electron will be about 1.1 times 10 to minus 7, it's minus 14, 10 to minus 7 seconds. So this is the travel time for the electron. Alright, now we are going to move the proton. For the proton, y0 is equal 10 and minus 10, while the y is minus 15, right? So actually the y minus y0 for the proton, delta y will be equal minus 5 millimeter because it is moving in the negative direction. So delta y, again we are going to use this equation, delta y proton will be equal 1/2 a proton times t proton squared, and this is minus 5 times, or just let me just write the equation first. From here, t proton squared will be equal 2 times delta y proton over a proton, and 2 times now minus 5 times 10 to minus 3rd meter over, what was the acceleration of the proton? It is like 4.8 times 10 to 8 meter per second squared, but it is actually it is in the negative direction, so we need to include this negative sign here. And from here, if we calculate, we can find it's going to be like 2.1 times 10 to minus 11 seconds squared. For the travel time, we need to take the square root of it. So travel time of the proton will be about 4.6 times 10 to minus 6 seconds. So this is the travel time of the proton. Alright, so this is the answer for part D. Now we are ready to move part E. Part E asking the work done by the electric force for electron and proton. Alright, so let me just clean this up. Alright, work done by the electric force on the electron and the proton. Alright, so this is our electron, the force in this direction, and also it is moving in this direction. And this is our proton, the force is in the opposite direction, but it is also moving in the opposite direction. And since these forces are constant, the work for F, E and P constant, and actually they were equal to each other. Remember when we calculated, we found the same magnitude for each forces, but of course they are in the opposite direction, so they are not equal as vectors. So, but work, since it is constant, we don't need to take any integration. F times S, or delta Y, will give you the work done by the electric force. So let's do it for electron. All right, the work electric force, work of electric force on the electron will be equal F electron times delta Y, and they are both positive, right? In the positive direction, and they are parallel to each other, so it is simply will be equal to magnitude of the electron force times the magnitude of delta Y, which is 5 millimeter. Again, we need to convert it to the meter to use it. All right, so if we plug the numbers, what was the force on electron? It is 8.01 times 10 to minus 19, its magnitude, Newton, times 5 millimeter, so 5 times 10 to minus 3rd meter, and we can just, you can use your calculator, we can find the work done by the electron is equal 4.0 times 10 to minus 21st joule. Alright, so 4 times 10 to minus 21st joule is the work done by the electric force on the electron. Now let's move to the proton. Okay, I'm going to clean this part up. Alright, proton. Now the work of electric force on the proton will be again equal to scalar multiplication of the electric force on the proton times delta y proton. And again, actually delta y is downward, but F proton is also downward. They are parallel to each other. The angle between them is 0. So using the definition of scalar multiplication, which is simply will be equal the magnitude of the proton electric force on the protons times the magnitude of the displacement of the proton, which is again 5 millimeter. And F proton is also equal to the electric force on the electron. So the same numbers, like 8.01 times 10 to minus 19 Newton times 5 millimeter, which is going to be 5 times 10 to minus 3rd meter, and the result will be the same, 4.0 times 10 to minus 21st joule. Alright, so in joule, see, it is that small number, alright, 4.0 times 10 to minus 23rd joule, but actually for this particle, it's a huge amount of energy, alright, it is given, don't forget. But joule, in this context, joule doesn't seem so much appropriate to use here. So we can define another unit here. We call it electron volt. All right, electron volt is the energy to the elementary charge. Elementary charge is 1.602 times times 10 to minus 19 Coulomb. The energy to elementary charge under 1 volt potential difference. So actually, like 1 joule, we can write it 1 times elementary charge, all right, times 1 volt. And if we plug this elementary charge into it, we are going to find actually 1 electron volt, 1 joule will be equal 1 times 1.602 times 10 to minus 16 electron volt. We call it electron volt now. And from here, we can write 1 joule or 1 electron volt will be equal 1 over 1.602 times 10 to minus 19 electron volt. Joule. Okay, so if you see this electron volt unit, you can use it. You can convert it to the joule by using this conversion. All right, let's move on to the part F. Part F is asking calculate the kinetic energies of the electron and proton after they move 5 millimeters. So part F is asking the kinetic energies of the electron and proton after they move 5 millimeter. One is moving upward, the other is moving downward. But I mean, for the energy is a scalar magnitude, so direction is not important. Now we can solve this problem in 2 ways. One is the classical motion problem. We can write like the equation of motion for the velocity. When our object is moving with an acceleration, I can write V will be equal to its initial velocity times its accelerations times the travel time. And we already calculated the travel time, acceleration, and we know actually they are starting from rest, so initial velocity is 0. So for the velocity of electron, we can just multiply with the travel time of electron and its acceleration, And then we can write the kinetic energy is equal 1/2 mv squared. All right, we already know the masses of the electron and proton. So after we calculate their velocities, after they move 5 millimeter, we can plug it into this equation to calculate the kinetic energy. All right, the other way is, this is first way, but it doesn't have to be the most practical way. We also know this as a second way, we need to remember the work energy theorem that we discussed in the first semester. Remember what this theorem tells us? The work done by a force will be equal the difference in the kinetic energy in the object. So actually this is kinetic energy final minus kinetic energy initial. So what are their kinetic energies in this problem? The electron and proton are at rest in the beginning, so they are not moving, their velocity is zero, so the initial kinetic energy is 0. So if you find this delta Ke, the difference in the kinetic energy will be equal their final kinetic energies after they move 5 millimeter. And we already calculate the work, so actually it is easy to write their kinetic energies. The work, the kinetic energy final of the electron will be equal the work done by electric force on the electron, and it was 4.0 times 10 to minus 21st joule. And similarly, work done by the kinetic energy of the proton will be equal work of the electric force on the proton, which is equal to the work on the electron, 10 to minus 21st joule. So you don't, if you calculate the work done by the electric force, now you don't need to calculate again the kinetic energy of the electron and proton, because that work will be converted to the kinetic energy of the electron and proton by work energy theorem. So actually, you know, part F is not actually a separate solution. You can follow a solution, of course, by following the discussion of motion we followed in the first semester, calculating its final velocity after they move 5 millimeter. We already calculated travel time for each. So plug it here, calculate their final velocity, and plug the final velocity into the equation of kinetic energy to find. Actually, it's a good practice to confirm this result by using the first way by yourself. All right, let's move on the next part G, and asking calculate the electric potential difference for the electron and proton after they move 5 millimeter. Okay, let me give you the figure again. We draw in the beginning. So this is our plates, all right? Point A, point B. VA was equal to 0 volt. We just choose it as a ground. VB was 100 volt. Let me just put the final location of the electron. Electron was here, 5 millimeter below of the positive plate, and the electron was here, 15 millimeter below the positive plate. So this is electron, this is proton, and now we know the electric field. We calculate the electric field, which is in this direction, 5,000 Newton per Coulomb. So the electric potential here, let's call it, this is dE, and here, let's say this is d proton, and the electric potential difference for electron will be equal E times the electric field times dE, the separation of electron from the positive plate and our ground. And for the proton, again, it will be equal to the electric field times the separation of the proton, which is shown with dP here. So part G, electric potential difference for electron and proton. Now, for electron, electron. The delta VE, I'm going to call delta VE the electric potential difference for the electron, will be equal electric field times the separation of the electron, the separation between the electron and the positive plate, which will be equal 5,000 Newton per Coulomb times 5 millimeter. We need to put it like 5 times 10 to minus 3rd meter, and you will find, let me check my notes, you will find 25 volt. All right, but for the electric potential difference for the electron is 25 volt. Now the similar calculations, but for the proton. So delta Vp equal now the electric field times dP, and it is 5,000 Newton per Coulomb times, it was 15 millimeter below the positive plate, so the separation is 15 millimeter or 15 times 10 to minus 3rd meter. So we can just write it is 75 volt, which is the electric potential difference for the proton. And now I think with this part, we're done with this problem. And next problem will be the 12th one. 12th one in the documents, which is about a charge object whose charge is given, which is shoot into an electric field, a horizontal electric field, by making an angle of 75 degrees. And you have this problem, so you can read yourself. I just read here, but I'm not going to write it. Now it is problem 12. All right. Now problem 12. In the problem 12, we have an object of mass of 10 kilogram and charge 1 millicoulomb. Is launched with an initial velocity of 10 meters per second at an angle of 75 degrees with respect to the horizontal uniform electric field, whose magnitude is 1.10 to 5th Newton per Coulomb. All right, and what is asking? It has 3 parts. One part is asking the calculate maximum height and the range of this charge object. And part, all right, I think I skipped part B here, but anyway, we can go yourself. And part C is asking what happens to range and the maximum height when we reverse the direction of the electric field. First thing is first. Let's picturize this problem. We have horizontal electric field. So I'm going to write the electric field like here. All right, this is the electric field. Let's say in this direction. All right, we are free to choose the direction, and its magnitude is equal, let me check the numbers. Its magnitude is 1.0 times 10 to 5th Newton per Coulomb. And we are shooting an object of mass 10 kilogram, let's say from here in this direction, and the angle is 75 degrees with an initial velocity 10 meters per second, and it has a mass 10 kilogram. All right, and it's going to move like this in this direction. Okay, we are gonna call this like H max, and also from here to here is going to be range, the maximum distance, or this distance from its shooting point along the horizontal axis. And we have this figure. All right, the electric field, horizontal electric field, whose magnitude is 1 times 10 to 5th Newton per Coulomb, and we are shooting an object into this electric field by making an angle of 75 degrees, the initial velocity 10 meters per second, and the object has a mass of 10 kilogram. And first part is asking what is the maximum height and range of this object. But before jumping onto the solution, let's first draw the free body diagram. All right, it's our object, Now it is moving along the horizontal, along the horizontal electric field. So what forces are acting on this object? First, the electric force, right? And the charge, let me just put the charge of this object. Q is equal 1 millicoulomb. All right, 1 times 10 to minus third coulomb. So 1 millicoulomb. Positive charge, so electric force will be in the same direction as the electric field. So these objects will feel a horizontal electric force along its motion. What else? It has a mass, so gravity is always in the game, and we can put mg in this direction. Anything else we are missing? I think not. So these two forces, and actually these two forces are perpendicular to each other. So electric force will will control the horizontal part of this motion, and the gravitational force will control the vertical part of this motion. Before moving, taking a step to the solution, let's also write the components of this velocity. So the x component of the initial velocity will be equal to v0 times cosine 75, and y component will be v0 times sine 75. Actually, we know the values, so if you use your calculator, you can find the x component is about like 2.6 meter per second. This is 2.6 meter per second, and this is gonna be, if you use your calculator, 9.6 meter per second. We are going to use it. And once again, let me make some space. And also this is the picture. All right, I'm going to redraw it when we need it, but I need some space now. Before again moving, let's also write the equations of motion for this motion. Actually, this is a kind of projectile motion, right? But what is the difference in the projectile motion now? There we have a horizontal force. So this motion, this projectile motion, also doing an accelerating motion along the horizontal one. Okay, this is the difference from the usual projectile motion. So we need to write the equation of motion for the horizontal part. Let me just write it. So x will be equal x0 plus v0x times t times 1/2 axt squared. So vx, the x component of the velocity, will be equal to x component of initial velocity plus ax times t, since we have an acceleration along the x-axis, and ax is constant, and here actually electric force, right, over the mass of the objects, and electric force is q times the electric field over the object. Okay, and also we have horizontal part of this motion. So equation of motion, y will be equal to y0 times v0 yt plus 1/2 ay t squared. The y component of its instant velocity will be equal its initial velocity, y component of initial velocity times plus at times t, and ay is nothing but only the gravitational acceleration. All right, if I write it as a vector, and it is going to be along the positive x-axis, so I. All right, so we are going to use this to find the maximum height and the range of this object. Okay, so first of all, maximum height. Let me use red because the blue is fading away. Okay, maximum height. When y is equal h max, we know the y component of the velocity of the objects will be equal 0. All right, and from here, how we can find it? We can use that equation to find the time when it is going to reach up to the maximum height, and then we can use the time in this equation. So Vy is equal to V0y plus Ay times t, and it should be equal 0 when the y is equal h max. So from here, 0 will be equal what we found for the y component, 9.6 meter per second, minus, because the acceleration is minus g along the vertical motion, 9.81 times t. If you use your calculator, you will find the time will be equal here 0.98 seconds. So if you plug this here into this equation, forget about y0, we can assume that the point is, the shooting point is at the origin, so y0 will be equal 0. But now you know what is y0, the y component of the initial velocity, time, we just calculated it, you know the acceleration ay and t squared of this value. So you will, if you plug it into y equal y0 y times t minus 1/2 gt squared will be equal h max. And if you plug it here, I just give you the result. H max will be equal, 47 meter. All right. I suggest you to check my calculations and get this result if I make some mistakes in calculating. All right. So this is H max. Now we are going to calculate its range. All right. And for the range, we are going to use the horizontal part of this motion. And range is actually just maximum distance from the shooting point, horizontal distance from the shooting point. So when x is equal range, I'm going to use capital R for range. All right. And actually the time for the range when the object is at the point, the furthest point, horizontally furthest point, the motion will end. So we need to use t flight, right? T flight, and which is going to be equal 2 times t. That is what we found for h max, right? So t flight will be equal 2 times 0.98 seconds. It is going to be equal, let me check my notes. Where is this? All right, I'm checking my notes. Okay, it is going to be equal 1.96 seconds, and I just need to plug that t flight into this equation to find the range. So range will be equal, x0 is 0 because we assume the shooting point is at the origin, v0x times t flight plus 1/2 ax times t flight squared. And ax is given here, q times e over m. And if we plug the numbers here, I can just write the value of the acceleration. Let me just check what it is. From here, it is about, let me see my notes, 10.0 meter per second square. You just need to calculate. Q is given 1 microcoulomb. Don't forget to convert it to coulomb. Electric field is given. All right, it is 1 times 10 to 5th Newton per coulomb, and mass is given, which is 10 kilograms. Just plug it here. You can calculate the acceleration, x component of the acceleration, about like 10.0 meter per second square. So if I plug it here, the x component of the velocity is equal, we found 2.6 meter per second times 1.96 second plus 1/2 10 meter per second squared times 1.96 second squared. And if you plug them, you will find 24.3 meters. All right, so actually it is going to move that much horizontally, 24.3 meters, when it is getting out of the electric field. So this is the furthest point, we call it range, and actually this is the part of problem 12 to answer. The last part is just reversing the electric field and recalculate the H max and the range, the maximum height and range. Actually the solution, the strategy will be the same, but the answer will be different, of course, the results. I leave it that part to you to solve.
but let me just picturize it for you. Part C. Alright, part C is reversing the direction of the electric field. Alright, so now the electric field will be in this direction, alright, but we are going to shoot the same object in the same direction with 75 degrees, alright, V0 was equal 10 meter, I think it was 10, right? 10 meter per second. The masses, the charges are all the same. Now asking calculate the H max and range after we reverse the direction. So I'll leave you the solution because the steps will be the same, but the results will be different. So it's a good practice to follow by yourself. Okay, so another problem for the motion in an electric field, which is given in problem 14. All right, you can check yourself from the document, but I'll read you to a problem. All right, in the problem 14, we have an electron which is dropped at a point 10 centimeter above a charge ring center of 6 centimeter diameter, whose total charge is is equal 5 microcoulomb. All right, first let's picturize it before reading the parts. We have a charge ring like this, all right? Its diameter is 50 centimeter, so the radius will be equal 25 centimeter or 0.25 meter. Okay, we need to convert it to meter. And we have an electron here, you know the charge of the electron, which is negative, and it has an elementary charge 1.602 times 10 to minus 19 coulomb, and the total Q distributed over this ring is 5 microcoulomb. We need to convert it to the coulomb. And first part is asking to define the motion of the electric field. So this is positive charge ring, this is negative charge, so the force between ring and the electron will be attractive, right? Let me remind you what is the electric field of this ring. Let's call it first Y, all right? Y is the distance of the electron from the center of the ring. So if I write the electric field of this ring with respect to Y, which we calculated in one video, like K, the Coulomb's constant, Q, the total charge of the ring, Y is the distance between the center of the ring and the electron, over R squared plus Y squared, 3/2 J. J is the unit vector along the positive y-axis, and remember the electric field of such a ring is always perpendicular to the surface of the ring, okay? This surface, I mean. So the electric field will be in this direction, all right, upward, but since electron has a negative charge, the force on the electron will be in the opposite direction. So let's just define the motion of this electron, okay, around the ring. Now I have the electron here, and I'm going to just drop it. I'm going to release it, okay? And once I release it, it has an initial velocity 0, but since the electric force is attractive, it starts moving toward the ring. But since it is moving, Y is getting shorter and shorter, so electric field is getting weaker and weaker, and when it comes to the center, the electric field, Y is equal 0, the electric field will be equal 0. So there is no force when the electron is passing through the center, but it has some velocity, right? So it's not going to stop here, so it keeps moving toward, and here the electric force will be attractive, so electric force will just switch the direction. The electron starts slowing down, and at some point it's going to stop here, okay? But it has still the force, so it starts moving back to the ring, and then coming to the center, again zero electric field, zero force, but it has some velocity. It keeps moving upward, come to that point, stop, and then actually it's going to oscillate or vibrate around the ring. Okay, it keeps moving up and down, up and down. All right, so this is the definition of the motion of the electron. Actually, it's going to move, it's going to make a periodic motion. We call it vibration, all right, or oscillation. So it is going to move up and down along the thing. Of course, we assume no friction, no other things. So this system is isolated, and there is no other electric field. We have only electric field of the ring, and it is the definition of the motion. Now, so this is the answer of part A. The electron oscillates around the around the ring. It moves when it is passing the center. There is no electric force on the electron, but it has some velocity, so it cannot stop here. It keeps moving down, come to here. At some point, it's going to stop, but there will be a force attractive, which is taking the electron back to the ring. So it starts moving upward, coming to the center again. Zero electric force, but now again it has some velocity upward, so it keeps moving. And stop again, so it keeps moving up and down as an answer of part A. Now, part B is asking what is the work done by the electric force when the electron passes the center. So actually part B is asking work of the electric force between the initial point and the center. Okay, and now we can write the work like the electric force times the path. Let me call it ds or dy, right? Here is dy, but the force is not constant, right? Y is if y changes, the electric field changes, so electric force will be changed, and I can write the electric force by using Q, electron charge, and the electric field, which is simply like K, Q, and E is the charge of the electron, which is elementary charge, over R squared plus Y squared, 3/2. We have Y here, and then J. All right, this is the electric force on the electron. Don't forget, this is negative, all right? E, let me put the negative here. So it is downward. All right, so we need to integrate this electron force between Y and the center. At the center, let's assume that Y is equal to 0. So once we integrate it, the result will be the work done by the electric force. So let us write it. Fe is here. Let me put minus K, Q, E. These are constants, so I can put out of the integration, and that's, I think, it. From Y to 0. Y is given in the problem actually. It is 10 centimeter. Okay, Y is equal to 10 centimeter. We need to convert it to the meter at the end. All right, so it is the rest of the part Y over R squared plus Y squared 3/2 dy. Okay, let me make myself some space so we understand this part. Just clean this up. All right, so actually this is an easy integration. So work, after we integrate it, the work will be equal K minus KQE minus 1 over square root R squared plus Y squared, and from Y is equal 0.1 meter. It was 10 centimeter, but we need to convert the meter to 0. So if I put it here, actually just we need to put the numbers now. If I put it, it's going to be minus will be positive. So it's going to be like K, Q, E, 1 over R, Y is equal to 0 minus 1 over R squared plus 0.1 squared. Okay, R is also given 25 or 0.25 meter, 25 centimeter, but 0.5 25 meter. So if you plug the numbers, we have E is equal, just let me remind you here, E is equal 1.602 times 10 to minus 19 Coulomb, and I already put the negative sign out of it, so it is positive here. And if you plug the numbers using your calculator, you will find the work done by the electric force is about 2.8 times 10 to minus 16 joule. This is the work done by the electric force when the electron is moving in the electric field of a ring. Alright, these are the problems about the motion in an electric field. Actually, you see, we use the standard treatment, equations of motions. We already discussed the motion in the first semester, Newton's laws, mechanics. Actually, we are using all of them. The only difference from the first semester is now we have the force generated by the electric charges or given in terms of the electric field. But all the rest is the same while understanding the motion of a charged object in an electric field. So let's take another break here. We are going to move to the electric potential energy and electric potential in the next part.